give it a start here. This morning we're first going to hear from Tom Clooney on the calendaring system, which basically controls changing rotation rate, if you want a tidally log system, etc. And Tom should be online. I'm going to change to your presentation, Tom.
Okay, I sent a new one just a few minutes ago. Did you get it?
I got it. I'm on it. As long as you didn't send me two new ones.
No. Just, it was one about 5 before the hour or whatever it was.
Awesome. Okay, so let's see how this. No, it's showing.
If you go to the model, it's model E,
Tell it to
documentation type. Okay. And that's sort of like the
not to do it that way.
section. So I'm running the model, but it also has sections. Maybe just go. Yesterday I couldn't. But it is all written down. It's just
Presenter view.
everything's written down.
Well, you have a PowerPoint.
Yeah. How do I get it?
And also because it's so extensive.
Yeah, it stopped.
And then present. Oh, but if you don't present, it goes down. That's okay. I'm presenting.
And every time I have a problem, somebody looked at this.
Slideshow.
Oh, slideshow. Obviously.
Yeah.
I could try.
The other thing you can do if you just want to, one program called NCDF, which comes with the net CDF files, and I don't know, you should have that.
Wait, so now you do.
Like I'll do the IAJ file.
It's a Mac. How do you
Basically,
I don't know. Switch.
metadata is you pipe that into a more or something that tells you all the variables and their dimensions.
How can I do?
So this tells me that. Yeah, 72 latitude.
Okay, Tom, are you there?
I am. Can you hear me?
Okay. All right. Let's go ahead and start. I think your presentation's up.
Okay.
We're all ready to go.
The rest of the speakers can thank me because there's nowhere to go but up after this. So topic we already have. I guess you'll have to do the slide transition for me, Mike?
Yes.
Okay, so next slide. Okay, so the basic idea here is that for an arbitrary exoplanet, we have an orbit that's determined by physics, but we want to have some calendar that has some relationship to that orbit so that we can make correspondences. In particular, we'd like, the seasons for this exoplanet to correspond to the months that we're used to thinking about for the Earth. So on the orbit side, the kind of things that the model gives back to us are like distance from the sun, the hour angle for the planet, the declination of the tilt. And on the calendar side, we want to be able to get things back like what year is it, what month is it, date, day of year, hours, and seconds. And we want these things to correspond to each other in some nice and elegant way. All right, next slide. So we have a lot of arbitrary ways that we can make this association. And so what I'm going to describe here is the one that was decided. It's very climate-centric. The idea is that we look at the Earth orbit on the left. There's an angle that's subtended by the planet in each of the months. Now, these are not equal angles because we're reflecting the actual calendar we use for the Earth. So February is going to be a smaller angle because of that. It also depends upon, some parts of the year we're closer and such. But what we're going to do is we're going to keep those angles the same for the exoplanet. And all of these angles are measured relative to the spring equinox. So you're going to find that the spring equinox always falls in about 2/3 of the way through March on any of the planets. If you ever see something going wrong there, it's a good sign something deeper went wrong, and you're going to want to contact me. But this is the basic picture, and I've purposely drawn the exoplanet to be more perverse. You can see that it's quite possible for the spring equinox to be happening someplace where the orbit is actually quite far from the sun. The Earth is sort of unfortunate because the perihelion comes so close to the winter solstice that it gives you sort of an unrealistic view of what goes on in general. In particular, we think of this, the 4 seasons as being roughly equal in length, but on an exoplanet, that doesn't need to be the case. All right, that's on the orbital side. Then for the rotation of the planet itself, we divide days into 24 equal hours. Now, you'll see a lot of other groups that instead they keep the length of an hour being 3,600 seconds and then have a varying number of hours, and you'd have to have, this exoplanet has 15.7 hours per day and such like this. That's not the approach we did. Again, it's sort of thinking of the angles instead. We're keeping the 24-hour clock, but an hour may not be 3,600 seconds. And then finally, sort of an obvious convention is that the hour angle is 0. For the prime meridian, I meant to say, it's basically it says it's midnight on your prime meridian at the beginning of the year, with a few caveats that we'll get to in the subsequent slides. Okay? All right, next slide. All right, this all works fairly well as long as the omega for the orbit is much smaller than omega for the planet, or alternatively, as long as the rotational period of the planet is much less than the orbital period. And that's true for the Earth, it's true for Mars, it's true for a lot of the planets we're used to, but there are slow rotators out there such as Mercury, or Venus, more relevant, where this assumption is very, very badly violated. But where this condition is true, we can do some nice things. We can adjust the periods so that we can have an integral number of solar days per year. For instance, on the Earth climate model in Model E, the Earth configuration, we use a 365-day year. This is a pretty good approximation to the real year, which is about 365.25 days, and we don't really worry about that. We can do similar adjustments for things like Mars, but as we'll get to, for Venus, that's not so nice. It also means that we can have 12 months in our year that each have multiple days. If you start getting to a very, very slow rotator, this starts to be a problem. Okay, so next slide. All right, so the compromise that was done to support slow rotators and not have the calendar become sort of degenerate was that we're always going to have at least 120 calendar days. In other words, if you have an exoplanet who has fewer than 120 solar days in the year, the calendar days and the solar days are not going to be the same anymore. And all of our diagnostics are based upon calendar days. So you have to start being very wary of interpreting anything which looks like a diurnal diagnostic. You also have to be careful as you get more extreme that the monthly averages can start to be misleading. Right now, any given month on the Earth has roughly 15 days and 15 nights in equal measure, unless you're sort of, near the poles, near the solstice and such. You could have, for a slow rotator, you could have a month where even at the equator, this part of the planet was in daylight for the entire month, or most of the month. And so you can get biases at the monthly. So the monthly averages may not do what you think in some of these cases. And then when you get really slow, it becomes inappropriate to adjust the periods to get an integral number of solar days. So in Venus, the day is actually longer than the year, and you would not properly capture what's going on there. On the other hand, it's got very low eccentricity, so maybe it doesn't matter as much. So we have a way of deactivating this integral relationship. And when you do, you have to remember that the seasons now float from year to year. January 1st, will be, winter time by, solar longitude at the beginning. But later on, January 1st is going to be an entirely different part of the orbit, just because now the calendar year is just different than the orbital year. Okay? Am I saying that right? No.
Sure.
Yeah, because we're still going up by days. We can't, years become sort of meaningless in the calendar now. So what this really means is the next bullet. You have to run a large number of years to get valid global averages. A single year might not even be a full day. So you typically might need to do 10 or 20 years to get both a consistent number of days and a consistent number of years if you have large eccentricity or large tilt. Okay, next slide. All right, so here are the parameters that are supported currently in Model E. The first one is planet name, and this is largely a safety measure. If you don't set this one, then everything is going to default to the climate model for the Earth. You're going to get just Earth-like things, and the rest of these parameters are going to be ignored. So I want to emphasize that, because that sometimes people miss this. They set all these other things and don't see a change. Set the planet name to something, okay, not Earth. All right, then you can set the obliquity, how much tilt the planet has. This is in degrees, and if you don't set it, then the default is from modern Earth. You can set the eccentricity. That's just a decimal number, and its default is again from modern Earth. The longitude at periapsis, this is in degrees, and this is from the modern Earth. Default is modern Earth. Sidereal orbital period and sidereal rotational period. This is the one you probably play with the most often. These are both in seconds, and you'll notice that we're not saying the length of the day, we're saying the sidereal rotation period. So this trips people up occasionally. And so, and the slide is wrong here. So on that second line, that should be, no, I'm sorry. No, that's right. No, it's wrong. The sidereal period is not 24 times 3600. So I missed that. That was in last year's slide as well. Anybody know what that is off the top of their head? It's slightly less than that. Okay.
3 hours, 56 minutes or something like that.
So you make sure you multiply by 365 divided by 366 if you want to try to change that. Sorry about that. All right, and then the last one is this subtle one, and we require you to specify this. You have to say quantize true or false, and the reason we require you to do it because people were often confused, and so we figured force them to actually think that. So if you set quantize year length to true, which we usually recommend, then what the algorithm does is it adjusts the orbital period in a minimal way such that it becomes an integral multiple of the rotation period. And if you set it to false, it does not do that adjustment. So unless you have a very, very slow rotator, you'll have a much more natural interpretation of the calendar if you leave that set to true. But if you do have something like, you know, Venus, you're going to want to set it to false in order to get something even remotely like the real system. And then there's a few other parameters that we provide that you generally don't need to use. One is the mean distance. Its default is 1. It's in astronomical units in some sense. But the reason you don't usually use this is because Model E already has another parameter to change the amount of solar radiation hitting the planet. It's this S0X parameter you'll presumably hear about somewhere else. But if you want to have multiple planets for the same star system and you want to keep like SOX constant to represent the star for that system, then you could use this for each planet to have its own mean distance. So there are scenarios where it's natural. And then lastly is the hour angle offset. This is if your topography files, you want to put the sun at a different place relative to Greenwich, prime meridian, such. I'm not going to be able to describe this very well, but you don't usually need to use this. But if you want to be able to shift what your prime meridian is on your planet, rather than changing your topography files, it's easier to change this parameter.
Yeah, for example, I can just mention something about that.
Sure.
If you have a tidally locked system, if you take Earth as a tidally locked system, it will put the substellar point for your tidally locked Earth over the Pacific. If you want the tidally locked system to have the substellar point over another longitude on Earth, you would use this feature to move it. So we have run simulations where we moved it to Africa, over Africa, and you will have to change the hour angle offset for that. Go ahead, Tom, sorry.
And I want to reiterate what I said yesterday about the quantized year length, that if you do set this to true, it will change a little bit your time step, and you can find what exact value is used in the PRT file.
Good point. Good point.
Time step or
yes,
or
time step.
period of orbital period.
Yeah, it changes the orbital period, which affects the time step in order to have the.
Actually, I'll probably quibble with that slightly. Independent of quantized year length, then your chosen time step is going to be modified so that there's an even integral number of time steps in a calendar day. Quantized doesn't change that. It really should be based just purely upon the calendar day. Now, because quantized year length will change the length of the year, it will change the length of the calendar day and impact what that adjustment is. But in general, the model has to adjust your time step in order to keep an even number of steps per day. Is that right? Anybody want to confirm that? That's my memory of what's going on there.
Yeah, I guess that's kind of.
Is that consistent
Igor
with what you think, Kostas?
Igor agrees. I believe Igor.
Okay.
Well, it's about time steps per day. I guess that's right. I think.
Right. And just to be really, really clear, in case anybody cares, it's not just an integral number of time steps per day. It's an even integral. So you have to either have 2 or 4 or 6 or 8 steps per day. The conventional Earth model has 48 steps per day, for instance. Okay, next slide. Okay, just to give you something concrete to look at, if you go look at the Mars template, and I presume at some point somebody's going to do a walkthrough and show you what the run decks look like if you haven't already seen them, you'll see a. I'm sorry?
Go ahead.
You'll see a section in there that looks like this, and these are the parameter values for Mars. And so you should be able to start with this as your template and then make the changes for your planet. Okay, next slide. So a sanity check, when you start up the run, at the very top of the file, there's a bunch of orbital information that is spat back out. And you might want to look at that and make sure that it makes sense to you. And I will admit, even for myself who designed this, it's easy to get confused. We believe it currently works correctly, but there have been issues over time. So if it really, after thinking about it, still doesn't make sense, please contact me or Mike Way, and we'll try to get to the bottom of it. But you see there, it tells you how long your planet's mean solar day and what its rotation period is in more conventional units, orbital period in more conventional units. This is for Mars, so you're seeing those kind of data. Mean distance, this kind of stuff. But the stuff at the bottom is largely just regurgitating some of the parameters that you provided. And then the next slide, here's what it actually tells you what your calendar looks like for your planet in case that matters to you, okay? So you'll see that, you know, the length of month varies more for Mars than it does for the Earth because it's got a higher eccentricity. You see the total number of days is 669. And then one nice little friendly sanity check at the end is it also tells you the dates in this calendar for various orbital configurations. So when is the vernal equinox? So it's the 52nd day of March, for instance. And periapsis is I hadn't realized how similar it was to Earth in that regard. So periapsis still happens in December, right? So anyway, so that I think that's the end of my slides, and I'm happy to take some questions.
There are any? I should say that we have we have iterated on this over the years. We have found bugs because of runs that we did where things looked a bit funny in the illumination. And I believe that what we have now is pretty good. So I don't think we expect to find any major problems.
Yeah, so I want to elaborate a little bit. There's sort of two different categories of bugs we found. So the one that's really annoying is that the underlying representation of time, if we're not very careful, can do some integer overflows and some multiplies. And so that ends up with sort of just random effects. And so that now that we know to look for it, that's the usual culprit. I think we've now done something to prevent that from happening again, but it's not beyond reason if you had some bizarre orbital parameters that have poor alignment in terms of divisibility that something happens there. The other one is a more interesting story, though. There's a thing called the equation of time. I'm not going to go into great detail. You can Google it. But it has to do with the fact that the solar day, the actual length of the solar day in terms of the sun being at noon, you know, straight up, varies because of the orbit. So, you know, the orbit is faster during the winter when it's closer to the sun, and the orbit is slower in the summer. And this leads to the actual position of the sun at noon drifting around in the sky a little bit. And in order to get exact agreement with my new implementation with the existing climate model, I ended up having to turn that term off. Now, I didn't know it was called equation of time. I was just deriving it with some simple geometry, but I could see that that was the error, and so I took it back out. And then later on, when we did an orbit that was highly eccentric and we weren't getting the published results where the sun was supposed to actually reverse course in the sky and all these kind of things, we eventually, after a great deal of heartache, tracked it down to this issue. So now equation of time is in the model. I don't remember what we decided to do for the Earth, though. Does the Earth now keep that adjustment in its model? Anybody know? At any rate, it's important for the exoplanets, so it should be on for exoplanets.
Yeah, Daniel.
But I don't have to mess with the calendar if I want to do things like run a tidally locked planet with an orbital period of 10 days. So like, it's not even clear what a month then would be. I guess it's, I don't know, like
If
the current system can handle all that?
Yes, it can.
Okay.
So you said 10 days. What do you mean by 10 days for a tidally locked planet?
It takes 10 days to go around the star.
10 Earth days.
Yes.
Sure. 10
Right.
times 24 hours.
Right. So you would enter the appropriate orbital period, and you would give it the same sidereal period. That's what makes it tidally locked, right?
Yep.
Okay.
We've done many of those.
Okay, great.
And then a month is.
And then there won't be any need to do an adjustment in that case because it is evenly divisible, and so you'll get that. And then the calendar you will see has 120 days, and if there's no eccentricity, you'll see that the months, you know, February will still be shorter because February is a short month for the Earth, but they'll be very close to 10 days in each month is what you'll see. But they'll just be calendar days; they won't have any meaning, and so you'll largely ignore the calendar, but it will still spit one out just so you'll see that impact.
Okay.
Right, so I think there was a conscious choice to limit that to 120 days, not anything smaller, so that you're not saving monthly diagnostics for a 12-day orbit period where we're we're 1 day is a month or something like that.
Or even worse, in Venus, it's 2 years.
Some integral over some reasonably good time period for getting some climatological control. There's no perfect answer to that question.
There is a hidden parameter I'm not going to tell you about where you can change that 120. Mike Way has played with it a number of times, but the general rule of thumb is you're going to probably confuse yourself more than it will do any good to play with that. But you can actually generate a calendar that only has 1 day in January and then 11 months that have 0 days.
Well, I also played with it, and I said that sometimes it's convenient to have Earth calendar, so you can force the model to have Earth calendar if you're for some reason you don't care about compatibility of calendar with rotational rate, or if you have sighted a lot planet and you still want in terms of Earth days. But in general, we probably don't care.
Igor, did we ever enable that? I know we discussed it. I don't remember what we did with that, though. It wouldn't.
Oh, I did enable it for my moon runs, and I regretted it later, actually. It was convenient. It was convenient at first to have Earth days because Moon is kind of like close to Earth, so I want to think about that. But then I realized that that messed up my diurnal diagnostics, and later when I did all my runs, I realized that I cannot use diurnal diagnostics because the calendar I used was not compatible with it.
Right. This would be a harder fix, but long term we might want to think of the diagnostics being done just purely in terms of longitude angles and hour angles, and make the calendars purely for human convenience, but bin things by those things. And so then you could still have your Earth calendar for when you are, but you would bin things by every 15 degrees in the hour angle for your planet. But we're not there. That capability does not exist. So, but if anybody really wants me to, I can give them a hardwired calendar that's independent of the orbit. That's not a hard change.
Yeah, I should say also that in a paper that we published last year, it's called Climates 1, and then Climates of Warm Earth 1. We published it in AppJ. We ran a bunch of simulations with slow rotators to compare to the Yang et al. Paper from 2014. And I actually did put in that a table of how the planet was illuminated for the slow rotators, and you can see how that corresponds to the calendar. And that'll give you a much more intuitive feel for how this thing's working. It's the first time we did it. I'm sorry, I didn't think to do it in earlier papers, but that could be.
Remind me to include that in these slides next year.
Yeah, I will. Maybe we can add it to the slides this year and put it on our Google Doc.
Actually, we were talking about possible bugs in the model. We have a diagnostic which is called, I think, incident solar radiation on top of the atmosphere. It's a two-dimensional diagnostics, and it's very convenient to look at when you suspect that something is wrong with the calendar or with your orbital parameters. And maybe not necessarily the bug, but maybe you could set up something wrong. So basically, it's convenient to look at it and see if it's doing what it's supposed to do, because that's basically just radiation which planet is getting from the sun. So you can see like if something is shifted, or if you have some, like if you expect something to be evenly distributed and it's not, just to make sure that it's doing what it's supposed to be doing.
I would say that even more strongly. I would say it's more than convenient. I would say you should absolutely check the AIJ parameter, INCSW_TO. And that's how we found out when we were trying to do 3-2 spin orbit resonance for the first time. That's how we found out that we hadn't quite gotten the orbit right yet by looking at that pattern of it, and it's shortwave radiation. And of course, if you're going to do synchronous point, then to make sure that you really have a bullseye into the starlight in the place that you want.
And we have to give credit to Tony Dobrovolskis for providing the paper that we could compare to.
Well, right. Well, I think there's sort of, sort of an absolute authority on this. I mean, not the only one, but Tony Dobrovolskis has written a series of papers on resonances, various eccentricities, and another one for various obliquities as well. And there was, in fact, an exoplanet GCM paper published a few years ago that purported to be looking at 3-2 resonant planets, and they made a mistake showing the pattern of starlight in their paper, and Dobrovolsky saw it and wrote a rebuttal paper saying, no, you guys got it wrong. You don't have the order right. And so, yeah, I highly recommend that parameter.
Yeah, I remain deeply embarrassed that I actually got this right in the first implementation and then took it out and still didn't remember it by the time we actually encountered the issue.
So how do we get the the signal cycle from the ROCKE-3D output?
You still get monthly output from the model.
But how do we get the signal cycle? Is the signal cycle still the 12 months cycle?
Yeah. Yes. But the point is that each month might be very few data points. So you need to know, you need to be aware of that for your planet. But you will always get 12 months of output. Yeah.
So
essentially, the output will be split in 12 pieces, what we call months. And then how long is really that piece, each of those pieces depends on how fast the planet is rotating around the star.
Oh, so each year from the model output is still the signal cycle.
Orbit is split in 12 uneven pieces.
Yes.
And in particular, January, February, and March are the winter months. At least in terms of the axial tilt, if you have something highly eccentric, that modifies that. But so as long as you're reasonably Earth-like, these actually correspond to the seasons of your planet.
I see. Then for slow rotator, the diurnal cycle could be even longer than the signal cycle.
Yeah, the monthly diagnostics are useless in that scenario.
Yeah, so be careful with the diurnal diagnostics, exactly.
And even the monthly.
Even the monthly. Yeah.
Once you're slow enough.
How do we compare? Yeah,
so if you have a very slow rotator, unless you really understand what you're doing with the short months, you should be comparing multi-year averages, multi-orbit averages that will correspond to a mean seasonal climate of the planet.
Okay.
But then if you want to calculate seasonality of that,
we're not well set.
We run into the problem when we look at the annual mean. We saw like an 11-year cycle. It turned out it's from the diurnal cycle. So is there a way to remove the diurnal cycle?
Remove the diurnal cycle.
Otherwise, we will see like oscillation.
Of course, you'll see oscillation.
Yeah,
that's what the diurnal cycle is supposed to do.
Yeah.
Well,
Right. The point is, that the diagnostic situation in ROCKE-3D is clumsy with regard to that. You have days that are comparable to months or not exactly to months or whatever. So that when you look from month to month, you're going to be getting some convolution of parts of the diurnal cycle with other things. So you have to be careful when you're looking at diagnostic cycle.
Yeah, basically you have to find the number of months. You should contain integer number of your days. Then after you average over those, you basically average over the diurnal cycle. Example that way.
Yeah, the problem is if we want to do like a climatology, we even don't know how many years we should average to get a climatology.
Why?
Because there is diurnal cycle in the seasonal cycle.
yes.
Right, but that's a physics question, not a
Okay.
diagnostic question.
No, it's a diagnostic
Based
question.
on
But
your
Mike may
assumption
encounter
of
cases
the-
like this. So so
Go
this.
ahead, Tom.
Go ahead.
Say again.
Go ahead. You were starting something.
I wasn't. I was saying go ahead and speak.
Oh. So what you would ideally want to do is find a number of years that is an integral multiple of the number of days, right? So if let's approximate. Suppose the Venus day was 1.5 Venus years. then a 3-year run would average an even number of days and an even number of years and should be the climatology. But it's not exactly that. So if you want to do a little bit better, you have to choose a larger number of years that's a closer approximation to a multiple of the days. And you know, in theory, that might be a very, very large multiple in a much longer run than what you want to do. So then you have to decide whether you maybe want to choose to modify your orbit slightly so you can make it more evenly divisible. So adjust the Venus length of the day a little bit, or the length of the year a little bit, so that maybe 7 years is an exact multiple or something, and then you can do that average there. But other than that, we'd have to do some extensions. The diagnostics are not well instrumented for that scenario. It's not impossible to reconsider, but it'd be a lot of work to try to get the diagnostics really looking at the hour angle instead of looking at the calendar.
So for there is an average script called a sum file. Will that always produce the correct annual mean? Meaning it's weighted by the different days for
you
each one?
produce the correct mean of 12 files. So what these 12 files mean, whether those 12 files are enough to get a properly averaged annual seasonality, is a different story. Because if you are on Venus after an orbit that you had 12 files in the output, you haven't completed the full day yet. So some files is blind in terms of what it produces. You tell it, make a mean of those 12 files, and it does that. What that mean means is another story. Well, you might need to make a 20-year mean to get a proper annual cycle of the planet's climatology.
It doesn't have to be 12 files. I mean, it
can be any number
of files, whatever you decide. But of course, 12 files gives you your annual cycle.
So I just had an idea that might be useful enough to be worth doing. It would complicate our description of things, but most of the cases I presume that have this issue are going to be largely circular orbits. It might make sense in those scenarios to instead base the calendar off of the day instead of off of the year. So we can make one calendar year be exactly one solar day. And you would then get, you know, exact results for the diurnal average that people sort of want in those scenarios. You still have to probably run a lot of years if there's an eccentricity that causes, you know, an additional seasonality on that. Just suggesting it because that would not probably be a hard switch to put into the code to do that particular case. No takers? Okay.
Any other questions online or in the room about this? We did spend a lot of time thinking about how to do this. It was the least worst kludge we could come up with, just so you know.
Yep.
It's not like we just did this one day. Tom did a lot of heavy lifting. We had a lot of discussions in-house with one of our former Mars people who's retired now. And we do have some description in the ROCKE-3D Planet 1.0 description paper about this. Tom and I wrote the section for that on the calendar, so there's some description in there as well. And COSIS did just post a link to the paper that I led last year that has these pictures in it of what the installation looks like for a slow rotator. So hopefully that'll prove useful to you as well.
So what's the reason we picked 120 as a number?
It's, well,
Blame Gavin.
Let's not go down that alley.
No, I mean, it's a sensible number. The idea is that you want to have enough days in a month that you can, at least for non-slow rotators, do some sensible averaging. So 10 is a nice round number per month is sort of, I think, where Gavin pulled that out.
Yes, we've argued about this for years.
Right, so longer, okay, so coming back to the Earth analogy, longer than the time scale of typical synoptic scale weather variation. So you know, if a month is 2 days, and you happen to have 2 days like we've had here in New York, you're not getting a very climatologically representative picture of what New York's climate is like in May. Over 10 days, you have a better shot as sort of a minimum amount of time. It's not, this is not written in stone. It's just the choice that we've made that, as Mike said, is the least worst.
And the simple rule of thumb is by the time this effect makes a difference, you should start being very wary of diagnostics. You have to think really carefully about what the model is really telling you.
Any other questions? Okay, thank you very much, Tom, for dialing in. I will add Tom's slides with his permission, I assume, to the Google slides that we've been presenting.
Oh, now I'm going to feel guilty. I just realized I have to do an EDAA for this, don't I?
You do whatever you want. I don't care about this thing.
Oh, yes, Tom, absolutely. Should have done that 30 days ago, according to the IG.
Yes. I thought it was internal. Oops. Okay.
Anyway, yeah, but fix that small mistake that you found in the slide and send me another copy, Tom, and I'll post it.
Okay.
Yeah, and there was 356 days
instead of 365.
Oh, that was just a typo. Got it. Okay, we'll do. All right. Cheers.
Thank you, Tom.
Yep. Thank you, Tom. Cheers.
Tell people what it's like to work at NASA. NASA was audited by the Inspector General last year, and one of the recommendations, actually, they made it a requirement, but got some pushback from our director, Gavin. One of their requirements for us was that we need to submit not only papers that we publish, but talks that we are going to give for internal review by NASA 30 days before we give the talk.
Wait, who exactly is reviewing this stuff? Yeah. And are they critiquing the science or are they just rubber stamping it?
Well,
right, so they don't understand what they're reading.
In the IG's mind, we're each, and our colleagues down at Goddard and Greenbelt, are reading all of these papers that all of us write and the talks that we're about to give, and are reviewing them for scientific accuracy and to make sure we're not, advocating overthrowing the government or anything like that, or whatever. And we're supposed to do this 30 days even before we give the talk.
To say this is not followed very.
Yeah. I mean, who even registers 30 days before?
Yeah, right. Okay, so maybe we'll go for another 20 minutes, then we'll take a break. I thought we'd talk a little bit now about post-processing analysis of the data. So these are closest as possible. Maybe I'll let him
sure.
try.
I mean, Mike has his flavor of those plots. So something that came up yesterday a couple of times, maybe more than a couple, was how do I know that the model has reached equilibrium? And that's not so easy to say in a very strict way, but there are some key diagnostics that you can use to say that, okay, my model appears to be in equilibrium, at least for the general climate purposes. So the most important diagnostic probably is this top one that is called net rad planet. And I'm showing you different lines, so every color is a different simulation. It doesn't matter which one is which. And the x-axis is number of years of the simulation.
Or number of orbits, depending on what calendar.
Or number of orbits, yeah. So the
and by the way, this net rad planet is a diagnostic that comes out of the NetCDF AIJ files that you should have been able to create yesterday, hopefully. So
it is essentially the net of all incoming minus all outgoing radiation, or the other way around maybe. So essentially at equilibrium, you would expect that the planet is in radiative balance, so this number should be 0. As you can see, first thing is that there is a great degree of variability, and so it fluctuates by at least a watt per meter square up and down, but on a long average, you want this number to be as close to 0 as possible. For us, and it's kind of arbitrary probably, we want the absolute mean of this variable to be less than 0.2 watts per meter square, and then we are happy.
And averaged over 10 years or 5 years, depending on.
5 is too short. I would say at least 10 or 20 years, and then it depends. It depends on the fluctuation.
And it depends on the planetary regime that you're in as well. So when we were doing simulations for our hypothetical Proxima Centauri B.
We'll get there later. We'll get there later.
Get there later? Okay. I won't talk about it now.
So the easiest way to do it is that you plot the time series and you see how it looks, and then that will tell you how long an average you should be making. Maggie?
So when I plot net rad planet in Panoply, it gives me a map. It doesn't give me versus time.
So that's the annual mean of that. Sorry, that's the area weighted mean of that map.
Yeah, so it's net rad planet underscore Hemis.
Right, but Maggie wants to know how does she make that?
Well, actually, in Panoply, it shows you, at the bottom it should show you the averages, like minimum, maximum, and mean. So the mean value is the one which you want to look at.
Okay.
Alternatively,
but we will get
to
like very small.
extract that data, I guess.
We'll teach you how to extract that
Very
data.
small print at the very bottom.
I see it.
But that's not how you get the data. We will show you how to get
but
the
that's
data.
one of the ways.
I don't have to like manually think through each
you do
one.
not.
and especially for global means, the Hemis variables contain the global mean.
Yeah.
So there is every variable in the AIJ has a Hemis one. Right. So the first number is the southern hemisphere mean. The second number is the northern hemisphere mean, and the third number is the global mean.
We'll show it again in a little bit. Yeah. I promise.
So you plot this and you see when netrad planet equals to 0 and on a long averages, and then you say, okay, the planet in terms of radiative balance at least is at equilibrium. Now other diagnostics might take much longer to equilibrate. If you want, for example, to equilibrate the global hydrological cycle of the planet and you started from something really weird, it might take you thousands of years to be able to reach lakes and groundwater and in general where the water is in equilibrium. And so it really depends which part of the planet's climate you are interested in, and you can see, but netrad planet is a key thing. And then the bottom plot shows you for the exact same runs, the global mean surface temperature. And you see that there is a different fluctuation there. And but at the end, after equilibrium, you would expect that this diagnostic has reached some equilibrated point. Of course, it will not be the same for every planet. Every planet will be different. But at the end, it should be something that is fairly stable in the after a very long number of orbits.
It should be flat.
Should be flat. Should be flat with some variability, of course, right? Which is the natural variability of the model.
Models.
Different simulations. Yeah, different simulations. Some of them are different planets. Some of them are the same planet with different configurations. It doesn't matter. It's just different worlds.
Some are one you're familiar with, the P1SOM40. It's in there. The one at the bottom.
So the gray line you see at the top that is still not at 0. So it's the one we started simulating, and you see that after 500 years, it is still not in equilibrium. And I mean, that's about it.
Colby, you had a question?
So you guys mentioned yesterday about how you use the random seed or the different seeds for the random number generator. You won't see like large variation between different seeds, would you?
No, you shouldn't.
No, you shouldn't.
No. Okay. So you will see different. The lines will not exactly overlap, but they will follow each other.
The operative word is should.
Why is that one taking so long to converge relative to?
Because we put a forcing in, and these are actually tuning runs for Planet 2.0.
Okay.
So we have changed the forcing on the models, and if you change the forcing, therefore, where you start out will not be where you should end, and it takes the model a while to come into equilibrium.
And if you see all those long runs, the runs that have a very long name, they are all fine resolution simulations, so they equilibrate at a different rate compared to the two bottom ones that they have the M in the name, which is the 4x5.
Okay.
And plus, they are a different model, right? They are apart like 3 years of development, so maybe even more. So they are a lot of physics have changed. And the ocean is very, very different as well.
So our initial condition files are the same that we used basically for Planet 1.0, but other things have changed in the model. So it takes the model a while to figure out where it should be.
Is that mostly controlled by the ocean physics?
All kinds of physics have changed in this model. So we have to retune the model to give us the appropriate answers given the changes in physics, basically.
So the amount of time that you will need for equilibrating a planet depends on the slowest processes that happen on that planet. So the atmosphere adjusts itself fairly easily. So if you have in a desert world, then that will equilibrate very, very fast. If you have a world, water world with a very deep ocean, like 5 kilometers, you will have to wait for the bottom of the ocean to equilibrate, and that will take thousands of years.
And keep in mind that what we call a very deep ocean, as Costa said, is like 5 kilometers. That's probably about as deep as we ever want to go. We'll probably go a little bit deeper. But I think that the astronomer's definition right now of a dry planet, given the capabilities for inferring mass and radius and therefore density, astronomers cannot tell the difference between a planet with 5 Earth oceans, I think, worth of water, and a completely dry planet.
Right.
Okay, so what we call a big deep ocean is at the edge of what astronomers would say, oh, we can detect water.
So Earth is dry.
So Earth is dry. Okay.
Is there any plan actually to make the ocean shallower?
You can make the ocean as shallow as you want.
Yeah.
I'll show you some stuff later.
Then why do we always go the deeper one?
Because these are Earth simulations. So we use Earth's bathymetry, and Earth's ocean goes down to 5,000 meters.
But the answer to your question is, what science questions are you asking? And so you might want to ask, well, does making an ocean deeper or shallower change the climate? And if you want to do that, then you want to try both, for example.
It's a similar question with changing orography. Take away the Rockies and see how the planet's climate changes.
Okay. I could talk a little bit more about this just before we take a break. I thought I would show a few more examples. Maybe I'll just try to share my desktop. That'll be a bit easier. So here is an example. Try to go full screen here. This is a shortcut for. So this was an example of a run I did a few years ago of using a Venus topography with a 300-meter deep ocean. So I take Venus's present topography, give it a 300-meter deep ocean, so it has continents like Earth and oceans. And you can see here at the top that it came into equilibrium quite quickly. That's probably because I used a restart file from another Venus run, like I discussed yesterday. So it came into equilibrium very fast. It took a while for the surface temperature to come into equilibrium. You can see that it doesn't get flat until 1,500 orbits, or Venus years. You can see the albedo took a while to come in around the same time. And there's this parameter down at towards the bottom, the GWTR. That's the amount of water in the ground hydrology scheme of the model. And there you can see why I ran the model for so long. It really did not come into equilibrium until around 2,500 years, and I couldn't verify it until I got to 3,000 years. That's because I've changed the topography completely. I have to use a completely different river directions file. I have to wait for the lakes to equilibrate, and you can actually see in the mass of the water of lakes, it's still increasing, although slowly over time. So if you want to bring your system into complete hydrological balance, this is an example where you came into net radiative balance very fast, but you did not come into hydrological balance. So the lakes are still deciding essentially where they should go and where they should not go. So the model is still deciding between evaporation and precipitation where everything should reside. So keep that in mind. If you change the topography a lot of your model and you really want to know where the surface water reservoirs are located, then you have to wait. If you don't care where the surface waters end up being, then you don't have to be so fussy. about waiting for this particular aspect of the model to come into equilibrium.
Essentially, you will get fairly quickly where the lakes are, but you will not know how big they are. And that does not affect climate much because natural climate is not changing really.
Yes, that's right. That's right. So the climatology will be the same. I can show an example of that later. I don't have the plot with me. Here's another example which I thought would be kind of fun for everyone to see. Does this work? Yes. This was for one of the Proxima Centauri B runs we did in the paper that Tony led and was published in Astrobiology just a couple months ago. Took us about February. What was that? February, yeah. So this particular run is a Q-flux run. This was to compare to other work that people have done and will do. This is a 100-meter deep ocean. And what you see here is that net red planet again came into equilibrium fairly fast. Now, Proxima Centauri B has a very short orbital period. I forgot, what is it now?
11.2.
11.2 days. So maybe, I can't see at the bottom here, but why is this in the way? These stupid things. Anyway, this is orbits, okay? So not years. Oh, it went away now. I put years there, but it's really orbits. You can see after about 250 orbits, net relative balance came into equilibrium, and it stayed like that for the rest of the time. Most things stayed like that. In fact, they all stayed pretty long in this sense. I ran, it doesn't take too long to run 4,000 orbits when your day length is only 11 days. So that's why this one went 4,000 orbits. But I'm going to show you another example where we used a fully coupled ocean.
Did you look at day side and night side separately?
Day side and night side separately what?
For tidally locked planets, because the night side is only radiatively coupled to the atmosphere.
Yeah, yeah.
In some cases, I found that it can take a really long time for it to go into energy equilibrium, even though the day side instantaneously equilibrates.
You mean on the night side, it takes a long time to get into equilibrium? I didn't know. This is a global average, though. So if the night's not in equilibrium, it'll show up in the average. This is a global average. So if there's an imbalance on the night side, it'll show up here. And we're pretty strict about it.
In the thin atmosphere limit.
So the legitimate question is the day-night difference changing with time? We don't.
I don't have that plotted up here, but I can check it.
If the day side is much hotter than the night side, then the global mean temperature is completely clobbered by the day side. Same for the average energy balance.
The average energy balance. Well, down to the 0.2 watt level, depending on you say it's thin atmosphere. So what do you mean by thin?
Like Mars-like.
Okay, these are not Mars atmospheres. These are minimum 1 bar, and we've even done some 10 bar atmospheres. But yeah, I agree on Mars. That could be a problem. Yeah, Colby.
Like in that similar situation, are you able to adjust how the heat is distributed along or about the planet? Like, can you adjust like wind speeds or something to where you can have the heat be distributed more to the night side? Or
we cannot. No. We let the physics do that. We don't adjust the wind speeds in the model. That's what the physics decide where the wind speed should be. Here's an example. Maybe I can put them both up next to each other. I think that might be more useful. So I showed you this Q-flux ocean on the left, and this is a fully coupled ocean on the right with the same number of orbits. I think that's why I ran them both the 4,000, because I wanted to be able to compare them. And you can see in this case on the right with the fully coupled ocean, I've forgotten the depth of this ocean right now. I think it's 158 meters, but I could be wrong. This is E. This is the or no, let's see. This is B. This is the control room.
For B, it's 900 meters.
900 meters. So, I'm glad the principal officer remembers the simulation that I ran.
He was only checking.
I'm a little overloaded here.
The height's so different in the initial at time 0.
Yes, I will get to that. Okay. So first thing you can see here.
It's different, the initial one. They are both 0. Just move in different directions.
Yeah.
Oh, I see what you're saying. Oh, yeah.
So you can see here, first of all, that the net radiative balance of the planet took a lot longer to come into equilibrium. Before, it was done in 250 orbits, and this time it took almost 2,000 orbits until it came into equilibrium. You can see the same with the surface temperature. It took and before it was about 250 years, about the same as the radiative balance. But in this case, on the right, it took, again, almost 2,000 orbits until the atmospheric temperature became stable. The same with the ocean ice fraction. That's another diagnostic that we often look at for worlds that are a bit on the cold side, you can see that it took over 2,000, almost 2,500 orbits until that also came out to be flat. That was another concern we have. We want to make sure that we understand fully what the global ice distribution was in this case. Now, Maggie brings up a point about, and then on the left, you can see all of those diagnostics came in very quickly for the Q-flux ocean. Now, Maggie's bringing up the point about the sea height changing. That's again an issue. I'm not have a good answer for you here why the sea height is changing, because this is an aquaplanet and that actually shouldn't change. So I don't know if there's something wrong with this diagnostic. This is a script that I run on all of my simulations, and so sometimes I'm running things that are probably not appropriate, but it's as I think I said yesterday, the sea height diagnostic just should at least tell you if you have continents. These are not continent-based worlds. There's no land sea mass here. It's pure ocean. The sea height will just tell you if water from your sea is ending up, say, in land-based reservoirs like lakes. We don't have that here. So I'm not sure what's going on in this case. As you can see, we don't have the answers to all of your questions. But it definitely has changed. But the land sea mass never changes, as I mentioned yesterday. Even if the sea height is changing, the land sea mass itself will never change in these worlds. We don't have a way to interactively change land surface types. So if the sea volume goes down and the Bering Strait becomes exposed, in theory, we don't see that in the model. Our model is not capable of doing that at the present, and we don't know when that will come in.
When you form or destroy sea ice, you should be losing the water, right?
Yeah.
So the sea height should be affected.
But no, because sea ice and
it flows, but doesn't contribute to the.
I don't think it changes the height, as far as I know.
I think the height is calculated by the bathymetry and the volume that you have as liquid water. So if you make ice, liquid water goes down, I think.
Thermal contraction?
Could be some thermal contraction.
Incorrect.
What?
Well,
Changing with temperature, but not ice initially.
Yeah, I should probably plot up like CSI, which is the thickness of the sea ice. That could be an interesting diagnostic. That might tell us something about what's going on here. And often I do plot that. For some reason, I don't have that.
I don't know if I didn't check the code.
I don't think it does that.
It's a very small number.
No, the number's right.
Yeah, but here it goes to 50%.
Sea height is going up.
Yeah, but I'm saying that for us it's.
No, right, but it's going down.
Right. That part. Yeah.
Yeah, but on the left, okay, sorry, that diagnostic on the left is meaningless because that's a Q-flux ocean and that's a static ocean. So I don't think that, I'm not sure that is.
Like you literally can't change.
You can't change that. So I
So
think
yeah,
that's
so the sea height in Q-flux ocean is something that one of our developers here, Max Kelly, said he does not know what this diagnostic is in the Q-flux ocean. We should not be looking at it.
So I apologize for plotting that. This is an old plot. Just actually, this is only for internal uses. We don't even publish this stuff. It's just that I put it up to make sure that what I produced makes sense. And yeah, the sea height in the Q-flux ocean doesn't really function. Okay, so I just wanted to cover those very quickly. Let's take a break again for say 15 minutes. Is that okay? And we'll come back and we'll talk some more about some other things.
Is that all you're going to say about radiative equilibrium?
No, that is not all we're going to say about radiative equilibrium. We're going to talk more. Okay. Don't worry. I'm going to give you more than you want. So I'll put us on mute for the next, see you at 1/4 after the hour.